Hurry up. So,
yeah, I heard some other people just think they did that.
Yeah, it was either carbon or developmental sounds easy. I'm barely sitting by that.
54 questions on the test, so it's a little longer. And then also remember after the test we're doing the assessment. That's 20 questions. That won't take very long. It's going to cover everything. So as I told you before, that I pull questions from all the tests. So I pull about 13 questions per test. One or two extra here and there. But they're taken directly from the test. So I'll give you a different circuit, but it'll still be a circuit. I'll give you a different force configuration of charges, but still determine the force of the particle.
So same topic.
Same topic, but I can change the question, right? Or, I ask about circuits in parallel in one question, I'll ask about circuits in series in another, that sort of thing. So as you're going through the old test, make sure that you're aware of that and that you ask yourself the question, how could he change this in order to come up with a new question? A good example of how I might change is if you look at the last exam, you'll notice there are two versions of the exam. Yeah, so those are good examples. They were very similar questions, they cover the same topics, but they were different. So that's a good example of how to expect the questions to change. Look from one question to the other and see how they change. Now I'll change them again for the final, of course. So I don't think there are any that are identical. So if you see a question, there might be one or two. But just make sure that you read them carefully, because you'll be very familiar with the 4 exams from this semester. So just be very careful that you read them. I try to highlight and italicize and bold everything that's important, that's less subtle, just to be clear that you read that carefully.
I feel like I'm going to end this class with an 89.5 just here.
No, I don't.
Because I have evolution on the same day, and it's horrible.
Right. 89.5.
So you said you didn't copy and paste like any direct questions?
I might have done one or two, but I'm pretty sure I changed all of them. Okay. Okay. Questions? We'll start with exam 1, okay? And then we'll go through the 4 exams. But largely I'm just here for your questions. There's so much material, I can't really go through all of it like I usually do on these help sessions. But we'll go through the old exams. Again, if you want to look back at the other old exams, that's fine. And all the questions are similar, honestly. So if you want extra practice, you can go back to the other old exams. But if there's a topic that's not on our 4 exams, it will not be on the final. And there aren't that many topics that we miss, but there are a few. Okay, so exam 1 dealt with forces, fields, and potential. You'll have some questions about the sort of basic, what do these charges do, that sort of thing. You'll have some questions about determining the force on a set of particles, given 2 or more particles. Look very closely at these things for symmetry, because often if you have symmetrical configurations, the problem is probably pretty trivial. Okay, we saw that in this test, where some questions you didn't have to deal with certain forces because they canceled out. You understand what I'm saying? Like, for example, this wasn't a calculation, but for example, on this problem right here, the forces due to these 2 particles canceled because they were equal and opposite. So just look for that on some of the calculations, because some of them they look very complicated, but they're actually very, very simple problems. Also, I try to give nice round numbers, so look for cancellations in the calculations as well. That'll give you nice round numbers. Remember your prefixes, your metric prefixes, nano, milli, centi, all that jazz comes up. Particular questions about this test?
Brian? Can you do like other variations number 4? Right there with the, like if it did touch or if it's positive.
Yeah, you could see stuff like that. Like if it was a positive rod, well, let's just sort of talk about what happens here. So if I have a negatively charged rod here, this is neutrally charged, and there are 3 electrons on here. So if I bring this negative rod up, the electrons all run down to this end. Only the electrons move, the protons don't move. So I get a net negative charge down here and a net positive charge down here. Right, so I just get electrons down here and protons down here. Now if I brought a positive rod up here, all the electrons will move to this end. I don't know how it's going to move it.
So it would attract it?
It would always attract it, yes. It would always be attractive, whether this is negative or a positive rod.
what if you touch it? Is that gonna
If you touched it, the negative charges would go onto the conductor, and then the wire would become negatively charged.
Okay, so it transfer electrons?
Right. So if you touched it, you would get an excess of negative charge distributed across the wire.
So the difference is if you touch it, you have more negative charge on it, and not how close.
Right. If you just hold it close, there's no transfer of charge. You still have an equal number of protons and electrons. It's just they're rearranged differently if you don't touch it. Now, if you touch it, you get an excess of electrons on the device, on the conductor. All right. I know y'all probably haven't worked through the test very much, but questions?
What about number 15?
Number 15. Okay, a charge of 2 coulombs at the origin. When charge Q is placed 2 meters along the positive x-axis, the electric field becomes 0. What is the value of Q? So I know that the electric field at this point, due to that 2 coulomb charge, is in this direction. Right? Because if I put a positive charge there, that positive charge will feel a force due to this charge to the left. So that's how I know that the electric field due to that charge is to the left and in that direction. The field then, due to that charge, has to be in that direction. That means, first of all, that this has to be a negative charge. But they're all negative. So now what I want to do is I'll say KQ over R squared here, and KQ over R squared here. Those two have to be equal. They're opposite, but they also have to be equal. So I just say KQ over R squared equal to KQ over R squared. The K's cancel. My Q's are different, so that's going to be 2 coulombs over R, which is 2 meters squared, equals to Q divided by 4 meters squared. And then you solve that for Q. All right, where the 4 meters was this distance, 2 plus 2. It looks like a difficult problem, but it's not that hard, really. You just sort of have to think about how the fields are.
How can you change that? Like, is there another way to ask that question?
Yeah, I could just shift the charges around. For example, like I could make this Q and this, some 2 coulomb charge or some quantity that you know. I could do them vertically instead of horizontally. That doesn't change how you work the problem, right? It's still the same. Something like that. I just wanted to see that you know how to do this process. All right? Is that clear, Montana? All right, what else? This test. I need to know how to do potentials and fields and forces. All that stuff will be on there. You'll need to know how to interpret the field lines. There are a couple field line questions on here. Yeah.
Is it 19 or 20, the one with the potential right there?
Yeah, number 20.
Do you do the potential energy stuff every single charge?
Well, this is different. So this is looking for the potential. I don't think that we had any potential energy problems, actually. Let me double check. Y'all know what he's asking? There are no potential energy problems. Well, I'll go back and revisit that question. But so this is a good example. That means you're not going to see electric potential energy on the test. But let's look at this question. What unnamed student is asking about for the recording, right? I'm not supposed to put your name on the recording. What you're asking about is U equals KQQ over R, right? Where we had this collection of particles and find the potential energy, but that's not what this is asking. This is asking about the potential at a point P, right? And that, when I say potential, that's my V. So in order to do this, you just say V equals the sum of KQ over R for each individual particle. But again, this is a nice case where I see that there's some symmetry where I don't have to do the whole calculation because I have a positive and a negative charge. Both are equidistant from point P, so I know that their potentials cancel out. So really all I have to do is just consider the potential due to this charge. So it's going to be 9 times 10 to the 9th, 10 times 10 to the minus 9, divided by this distance, which is the square root of 1 squared plus 1 squared. That's the square root of 2. Notice I do have some cancellations here. You'll often see cancellations just to make your calculations easier. So that's 90 over root 2, which is 64.
The only time the negative charge matters when we're dealing with potential.
No, it matters in all cases. For potential, though, potential is when you're, let me rephrase that. You include the negative charge only when you're doing potential. But the negatives do matter when you're doing fields and forces, but you don't include the negatives. You only use the signs to determine the direction of the vectors. So you never actually put the signs into the calculations, but you'll use them to draw the vectors. Let me show you an example. Can I clear this? That's a good question. So, like for example right here, I never considered that this was a negative charge, except when I said, well, the field due to that charge has to be in that direction. Because if this is a negative charge, then if I put a positive charge here, it will feel a force attracted. But at no point did the negative actually come into the calculation. But when you're doing potential, it does. Forces and fields, no negatives. Potential, yes negatives. All right.
Will you have a 19 real quick?
You're going to see a lot of these questions, right? You see these a lot anyway, but you'll see quite a few on the test tomorrow. They come out in various ways. Or it's not tomorrow, but you know. We're looking at electric field. So we first want to write down the expression for electric field. Of course, you'll have your equation sheet. You might want to look at that over the weekend, paste it to your bathroom mirror or whatever. All right? And then I look at what's being changed. Your distance from the charge is being halved. So then I say, well, this distance is being halved. How does that change whatever it is that I want to know about? And here I'm asking about the electric field. So if I have that distance, in order to make this equation still constant, I have to have a factor of 4 there. Because it's a half, it's squared, and it's in the denominator. 1/2 squared is 1/4, and 1 over 1/4 is equal to 4. You need to be very good at that, because it comes up a lot on the various tests. And it'll come up on Monday, too. All right? Is that clear? All right. Fields, are we okay on that? Okay, let's look at exam 2. We can come back to this if you have more questions, so y'all be thinking about it, but let's look at exam 2. All right, so exam 2, capacitors. You will have some circuits. Make sure that you're up on doing the circuits. So, for example, on this circuit, I could change it. I could ask, what is the charge across the 3 microfarad capacitor? I could change the values of the capacitors, or I could even give it as a simple parallel, just parallel circuit. So make sure that you're up on your circuits. It might be useful to go back and look at some of the other old exams, because it'll just give you a different variety of circuits to look at. But for the most part, if you know your circuits well, you should just be able to look at them and tell me what the answer is. Like, for example, this one, well, you might not be able to just look at this, but most of them you'll be able to just look at and tell me what the answer is, if you're good. Otherwise, take a little extra time and write out our various ways to do this. Yes, all this stuff. There will be some units type things. Make sure that you're up on your units. And then also don't forget our forces, fields, and potentials. But those have different units, right? Like, for example, potential is measured in volts. But since potential is energy per charge, it can also be measured in joules per coulomb. And then you could also express potential in its basic SI units, which is what? Energy over charge, that's kilograms, kilogram meters squared over seconds to the force, coulombs, something like that. Just make sure you're up on your units. It might be useful to go through and just sort of remind yourself of all the units. But always you can return back to the original equations and just plug in the units and determine the basic units. Knowing about voltmeters and ammeters, all these circuits, power.
Is the power equation on the equation sheet?
I'm pretty sure it is. Let's double check. right here. This is what you'll have on the test. So power is right here. It looks a little bit different. P equals I delta V. Change that, I guess. And then you have these alternate forms of the power equation, I squared R and V squared over R. All right, what on this test, y'all? Circuits. The rules for resistors, sort of how resistance varies with length, area, and resistivity. All this stuff is on the final. You will have simple resistor circuits. You'll also have more complicated resistor circuits like this one, or like this one, or this one. You'll have something about power and our circuit breaker and how that works. You need to know how all those devices work, the GFCI, the prong, the third prong, and the circuit breaker. All right, on this test, more questions? You'll feel okay with circuits? We'll take a look at a circuit. All right, let's just take a look. All right, let's look at this one. Which of these resistors has the smallest current? Okay. I can think about this in terms of numbers. Right. So first I'll have R1, 2, 3, and 5. R1, R2, R3, and R5. I know R1 is not the right answer because it has the biggest current. All the current comes here. And then the current splits into three pieces. The smallest amount of current will go where the largest resistance is, because resistance resists the flow of electricity. So this one has 6 ohms, this one has a total of 3 ohms, and this branch has 2 ohms. So this one will have the smallest current, this one will have the next smallest current, and this one will have the smallest current of all. So know how a current is distributed throughout a circuit in this way. And so the answer to this one would be what? What now? No. Not B? Oh, yeah. I'm sorry. Yes, no, you're right. That's not what I said, but you're right. This one has the smallest current. Yeah, R2. No, that is what I said. R2. Okay. Yeah, so, but for example, like if this was a 6 ohm resistor right here, that would mean R3 would have the smallest current. You'll follow me on that? Because now this branch has 7 ohms. So this branch has the largest resistance of the branches, and both of these resistors have the same current. So this resistor, even though it's smaller than this resistor, would still have the smallest current. Got me? Got it? See some stuff like that. Make sure you're up on circuits like this. You know, on a circuit like this, it often helps students to just redraw it. So you will see sort of a funky circuit like this. Draw my 2 ohm resistor, and then I have a parallel branch with a 1 and a 2 ohm, and then a 6 ohm like that. So this is my 2, 1, 2, 6, and this is 12 volts. So it might help you to redraw it like that. Really messy, just like I do it. And then you want to know the current through the 1 ohm resistor. Now hopefully you can just look at this. You can say I have a 6 and a 3 ohm resistor right here. Those combined give me 2 ohms, right? Because 6 and 3 and 1 over 6 plus 1 over 3 is 1 over 2, inverse of that is 2. So this is 2 ohms and 2 ohms, I have 4 ohms total. That means I have what through this resistor? I have 4 ohms here, 12 volts here. What's through this resistor? What current? 3 amps, right. So I have 3 amps here, and then I have 3 amps split between these two. 3 amps will be split. The smaller current will go here, so 1 amp here. The bigger current here, 2 amps here. So 2 is your right answer through the 1 ohm resistor. Of course, you can go through and calculate that the way we did, but that's the basic process. But being able to redraw those circuits is very useful because sometimes you look at this and like, what the heck is this? But if you redraw it in this way, I find it a little easier to analyze it. All right. Any other questions on this? Or just shaky topics? Circuits, sort of household stuff, resistance, resistivity, capacitor circuits. I'll go to the next exam, if not. All right, next. Huh?
No, go ahead.
Oh, no, go ahead. I was about to go to
We can
exam.
pause. I guess we have time.
Yeah, we have plenty of time.
Sounds like more complicated.
Yeah, so what is the equivalent capacitance of this circuit? No, not complicated at all, right? So here, look, we have a 3 and a 6 is what is 2, right? Because they're in parallel, they're in series, so it's 1 over 3, 1 over 3. A 2 and a 2 is 4, because you add them when they're in parallel. And then I have a 4 and a 4 is 2. 1 over a quarter plus a quarter is 1 over a half, which is 2. So my answer here is 2. You're going to see questions like that, like questions that if you're quick on your feet, you don't have to write a thing on the paper, okay? And you should be able to, well, maybe not completely, but for a lot of the tests, you shouldn't really have to write much at all. You just want to think. Now, I can also ask about the distribution of the charges here, or the voltages. You should be able to tell me right off, what is the voltage here? What, if I have a 4 and a 4, that means I'm going to have 6 volts and 6 volts. So I'm going to have 6 volts here. And then likewise up here, I'm going to have, let's see, which one gets the bigger voltage, the big capacitor or the smaller voltage? Yeah, right. So I get the smaller voltage here and the bigger voltage here. I know these share 6 volts. So I'm going to have 4 volts and 2 volts. Right. Being able to do that would really help. I'll work through it this way on the video. So if that's unclear to you, then maybe revisit those or we can go over it some more. All right? That's not too complicated, right? That's what it's going to be like. Any other questions on this? Do you have a question?
It's the one that was kind of complicated, not like, I'm trying to remember what one.
Okay, let me, on this test?
Yeah.
Number 7, the energy stored on the topmost 2 microfarad. No, this is just the energy is 1/2 CV squared. That's 2 microfarads. V is 12 volts squared. Because they're in parallel, I have the same voltages on the battery, 1/2. So that's 144 microjoules. You have that equation on your equation sheet. I mean, I say none of them are complicated, but, you know, some people didn't do very well, so, yeah, it is complicated, some of it. Any of these standing out to you? This one is sort of trips people up, but you will see questions like this, so be prepared for it, where I give you a voltage across one of the resistors, not the voltage across the power supply, but voltage across one of the resistors, and then you have to tell me something about the rest of the circuit. Maybe what is the voltage here, or what is the voltage across one of these. So here I told you have a 3 and a 3, 6 and a 2 here. This, by the way, simplifies to what? A 3, 6 and 2 in parallel is 1. If you don't believe me, try it out, but 1 over a third plus a 6 plus a half, that's equal to 1. So those are good numbers to know, and you'll see those on Monday. So I have a 1 ohm and a 3 ohm, and I have a 6 volt across the 3 ohm. And here I was asking across the 6 ohm resistor, what is the voltage? But I could also ask, what is the voltage here? So look, the way you'd do this is you'd say, I have 2 amps on this resistor. And this whole thing is, what do we say, 1 ohm. And I also have 2 amps through it, because those would be in series, so they have the same current. And so the voltage here would be I times R. That's going to be 2 volts. So I have 6 volts here, 2 volts here. That means I have 8 volts there. You'll see some questions like that. I think there's one question where I provide you with a voltage or current on one of the resistors and ask you about one of the other voltages or currents, either on the battery or whatever. But you sort of have to work backwards on those. All right? This one? We just did this one. I think you were out. Okay. 2 minutes, y'all? Let me just redo it right quick. Okay, so the big thing is to redraw them. And here, So we want to practice this. Look back at some of the other old exams and see some of the other circuits. But these are the same circuits. I have 2 ohm, 1, 2, and 6 ohm. All right. And then once you redraw it like that, it becomes a lot simpler. The way you do this is you start at the big side of the battery and you go through, you say, I got my 2 ohm, goes into here. If I come to a break in the circuit, or a branch in the circuit, on one of the branches I have a 1 and a 2 ohm. That's what I drew right here. And then on another branch I have the 6 ohm. That's what I did here. And then it all comes back together right here and goes back to the battery. Being able to look at circuits in that way and redraw them will help you. Are you okay going from that point? Because once you get to this, it's easier. Yeah, okay. But that's a common way to draw circuits. So, okay. We go on to the next test, Joe? Probably test 2 and 3 were the hardest for the class. You'll definitely have a multi-loop circuit like this. It'll be a different circuit, but one of these, what is the equation, and then also what is the direction and the magnitude of one of the currents. So y'all know how to do the equations here? You'll be step through it? Yeah, so remember there are some rules here. If I'm going in this direction on the battery, I get positive. So here I would have positive 2 volts going in this direction. Doesn't matter about the current for the batteries, just what direction. Positive 2 volts in this direction, negative 2 volts in this direction. For resistors, it does matter the direction of the current. Here the current's coming in this direction. If I go from this point to this point, negative potential. If I go against the current, positive potential. Well, I'm going to draw this out in a second. Here, going up, negative potential, big to little, positive potential because I'm going against the current. So if I were to rewrite the equation for that left loop, starting here and going in this direction, I would have plus 2 because I'm going from big to little, minus 2I1 because I'm going with the current, minus 4 plus 2I2 equals 0. Minus 4 because I'm going from big to little, and here plus 2I2 because I'm going against the current. Might want to revisit those rules in your notes about how we determine the sign of the potential, because you'll definitely see a couple problems like this. And then also don't forget that the currents are in different branches. So this is current 1 over here. This is current 2 in this branch, and current 3 is in this branch. Also, when you're solving for one of the currents, then I make them really simple if you just choose the right loop. So for example here, if you're trying to find I2, I want to know this current. In order to do that, I would choose this loop. The reason I would choose that loop is because there's no resistor in this loop. So the equation is just a lot easier to solve because you only have one unknown. You don't have to solve the whole system of equations. All right, the other alternative is that I would give you one of the currents. So if there was a resistor here, I would just give you the currents. And you can find examples of both of those in the old test. You can see either. We had some in our book as well. All right. Make sure you know how current, voltage, charge all vary with time for capacitors when they charge or discharge. Did you hear what I said? Okay.
For that one,
Yeah?
the only graph it's going to be is A, right? If it's charging or discharging?
No. Well, for current.
If it's charged, A would be discharging and B would be charging?
Current, yes. No. Let me think.
This is not going to sense.
Yeah, so A is always the answer, whether it's charging or discharging for current. But if it's something else, like if it's charged, for example, like if these are all Q, let's see, Q, this, like if this was Q, this would be charging, right? Because the charge increases on the capacitor, and then this would be discharging. These two are never the answer. Okay? Look back at that's like, for example, that's a way that I could and would and did change this problem. Ask about either the charge, voltage, or current. So look back at those. When it's charging, yeah, when it's charging, it slowly approaches that maximum charge, and then it asks them to add that maximum charge.
If it's voltage, is it the same as charge?
Voltage, same as charge. Yes, because Q is equal to CV, and so the voltage is directly proportional to the charge. Yeah, I guess current is current the only one that follows that function? Yeah, the current is always going to go down, whether it's charging or discharging. All right? Make sure you can work these problems with your exponential functions. Make sure that you look at your equation sheet, right? They have expressions for charging and discharging. I think they're labeled on there. Is that right? Yeah, so these are all those. And they are labeled for charging or discharging. These can help you remember what the various functions are as well, right? Because this one is that one that looks like this, and the charging one is the one that looks like this, increasing or decreasing. So if you forget those functions, you can look back at the equations and think about them. And look, the current always has the same. I don't think this is right. Let's think about this. Okay, it shouldn't affect you. It's okay. All right. So you know your right-hand rule for all the various applications. The direction of the magnetic field in a wire, the direction of the magnetic field, the direction of a magnetic field caused by a wire. So for example, if I have a wire with a current flowing in this direction, the magnetic field is into the page, out of the page, like that. Thumb along the direction of the current folds around. Make sure you know the force, QVB, right? So for example, if I have a positive charge moving in this direction with a certain velocity, say it enters a magnetic field that's in that direction, then the force felt by this is going to be out of the page. Go back and revisit your right-hand rule. You'll have a couple problems, several problems that have to do with right-hand rule. The force is your thumb, right? Also, make sure that you're up on the solenoid. Let's see, where was the solenoid? I thought there was a solenoid on here. There is a solenoid. There is a solenoid on the final. It's really just an application of that wire. Let me go and prep you for it, okay? You ready? It's easy, easy peasy. Right? If I have a solenoid of wire and the current goes in like this, these are all the outer loops. So these are the loops that are out closest to you. If the current is like that, my thumb go in the direction of the current, like this, and then my fingers wrap around. You know what I mean? These blue parts are the part that's closest to you, and the ones that aren't labeled are the parts furthest from you. So here, my magnetic field inside the solenoid would point in that direction. You follow me on that? So it's really just an application of this sort of. No, not that one. But your magnetic field on this one would point in this direction. Inside the loop would point in that direction. Yes, y'all can do that? No? Okay, so here, I have this loop of wire. It's sort of hard to see. But imagine that you can't see the loops on the backside. All right? So I have this loop of wire, and where the arrows are the side of the loop that's closest to you. And so I let my thumb go in the direction of that current, and so each loop makes a magnetic field that folds around. So out on this side of the loop, it's in that direction, but inside of the coil, it's in this direction. the magnetic field is in this direction. So the question is, what is the direction of the magnetic field inside the solenoid? And it's going to be to the right in this case. If it was going the opposite direction, it'd be to the left.
So if the arrow was pointing up, it would be to the left? Is that what you're saying, opposite?
That's what I'm saying, yeah.
Okay, but I'm just in there.
Well, no, don't do that because, you know, it could be up or down, or I could have it in orientation. Just know your right hand rule. That's all you gotta do. Just know your right hand rule.
I think of it like this, if you're doing like this, then it would go into the page right here, and it'll come around.
Well, it does go into the page, but inside the loop, right? So if I have, imagine this is one of these pieces of wire, right? The side of the wire. And the current is going down. So the magnetic field around one of these pieces of wire is this direction over here, and this direction back here. So this side is inside of the loop. The picture's not very good. That's why you're not. Alright. So you. Look, like this one. Let's find one with something where you can't see the backside. Okay, this one's pretty good. So here, the current on the front side is going up. So I'll let my thumb go up, and then the magnetic field inside of the loop goes to the left in this case. You follow me? I could do this on the test? Okay. Alright. What else on this test? Probably have something like this, some variation of that. Yeah.
If it's a positive particle and it's going towards, it always goes opposite the way of I.
Is that true? I don't know.
I know that answer.
Well, let's see. Our magnetic field is into the page, out of the page. That's our magnetic field. And then we just use our other application right hand rule. B is down, B is out of the page, so yeah, it's going to go opposite the current.
If it's a negative particle, does that change it?
Yeah, it would go the opposite direction. If it's a negative particle, go the opposite direction. I would be wary of sort of learning all those special cases. Just learn the right hand rule. And apply it. All right? But you can do what you want. Okay, whatever. If it works for you, that's great. Okay? I know. All right. Mass spectrometer. You know how to do this. It's really just using the equation. You'll see it. Make sure you know your spectrum. Remember, not only wavelength, but also frequency, energy, all that jazz. And not just these four particular ones, but all the spectrum. I think y'all all know that, right? Electromagnetic spectrum. Okay. The history of light. What's this? Snell's law, law of refraction. Knowing what the index of refraction is, sort of these basic things. Total internal reflection. Anything standing out to y'all? There is no total internal reflection on these. Is that it? Okay, nothing. Are you still want to explain it? Okay. It's worthwhile actually because it does. There are no total internal reflection, but it is useful to know this. So I mean, here as I'm moving from a high index to a low index fraction, the light ray will move away from the normal, and with a fiber optic, it's such that the indices of refraction are enough different that instead that it bends all the way over, and then it actually bends back into the material. Now, you're not going to have any total internal reflection, but you will have things where I ask you, how are the indices of refraction different? Like these different cases, this light bends towards the normal, away from the normal. How does the indices of refraction compare? All right? Does that make sense? Okay. Anything else from this test? Like this one, number 5?
Yeah.
Okay, so this is a charging capacitor. All right, it's connected to a battery, and so it's charging. So you could look at your equation sheet. Your charging capacitor function looks like this. And so you just say Q equals big Q, that's your CV, 1 minus e to the minus t over RC. All right, so big part is just knowing what these values are. Q is your maximum charge. That's C times V. That's going to be 150 microcoulombs. And then 1 minus e to the minus t over RC. 1 megohm, 5 microfarads. It's going to be 5 seconds. Remember, you can drop those metric prefixes because they cancel out. And then t is at 10 seconds. All right. I forget what it was. I think it was 130. No, I don't remember what the answer is. But you okay calculating that in your calculator? Make sure that you are. You'll probably see one. I forget exactly if it was, but I'm pretty sure there was one on there. Okay? Is that clear? Andrew?
I think I didn't do the E right, like press the actual E function on the calculator, right?
Okay, there are 2 E's on your calculator. There's the number E, which is this, and then there's also the capital E, which is like a times 10 scientific notation, times 10 to the blah, blah, blah. The second one would be incorrect. That's the capital E on your calculator. And yeah, I would, just an exponential. It's not this one. See the E right there? It's that one. Alright? Just make sure you're up, like, practice it before you come to the test. Make sure that you can do those funky things. You don't use those very often. Alright? Next test, okay? Other questions here? Alright, next test was the one we just took. Probably pretty well on. We'll just look at the 2M, though the online was very similar. You will have a question like this, and it'll be sort of similar where some of the material is missing, but you have to infer it based on what the image is like. So remember, there's different types of images. In fact, it would be very useful for you to just know all the different types of images that concave and convex mirrors and lenses produce. Y'all want to know? Let me show you right quick. It's good. There'll be several questions where this will be useful. So for our mirrors, concave, convex. For concave, you have, actually, let's do them. I'll do concave first. It looks like this. Outside the focal point, there's my object. My image is right here. It is an inverted real image, inverted and real. If it's at the focal point, there's no image at all. And if it's inside the focal point, it's like this. This is the object, this is the image, this is a upright, virtual, bigger image. And then if I have a convex mirror, which is like this, here's my object, here's my image, this is a virtual, upright, smaller image. And then for lenses, you get something very, very similar. So I'm going to draw them right next to one another. I'm going to do convex lenses first, because they're like concave mirrors. They look like this. If I'm outside the focal point, my image is like this. That is a inverted and real image. It can be bigger or smaller. If I'm at the focal point, like this, I get no image at all. These are all in your ray diagrams, by the way. And if I'm inside the focal point, there's my object. My image is right there. That is a virtual, upright, bigger image. So you see it's the same as what I had over here. Similarly, this is the same here and here. And then for a concave lens, which looks like this, no matter where my object is, the image is always here. It's going to be smaller, virtual, and upright, which is exactly the same as our convex mirror. So if you learn one set, you know the other set. Just be aware that the images for lenses, real images are on the opposite side of the objects, whereas for mirrors, real images are on the same side as the objects. Knowing these will help you. Just because I'll ask some outright questions like we had on that test, what type of mirror or lens is this? And then also in doing some of the calculations, it'll be useful for you to know what type of mirrors or lenses produce what types of images. I'll give y'all just a second. You know your ray diagrams, you will have one mirror or lens where you have to find the correct or incorrect rays, like you did on this test. Pretty sure you had questions like this asking about what types of images are formed by what types of mirrors or lenses. But if you know these little rules, then those questions are really just testing that knowledge. Knowing your ray diagrams help with that. So ray diagrams help with this, but they also help with knowing this basic knowledge. I'll take this away. Yeah. All right, it's going away. All right, this is all the same. Like I said, knowing those diagrams will help you with stuff like that, which you will have. Brian?
For this one right here, I'm not sure, the ray one, the ray number 1 should have been up and parallel.
Yeah, ray number 1 should have looked like this. It should have gone up like this, as if it were originating from the focal point, and then parallel to the axis. You could have known that this one was incorrect, because I know that the image that's produced by this lens is going to be on this side. That my image is going to be there. Well, let's see, it's not going to be exactly right there. Where's it going to be? It's going to be where these three rays cross. If I draw these rays back, my image is going to be right here. But you see, ray 2 actually crosses right here, and ray 2 says that my image is right here, but it's not. You just need to know your ray diagrams. Go back and review your ray diagrams. This was a particularly tricky one, right? This one's just a difficult one to do. One on a test, simply. But remember those rules for your rays. Does that answer your question? Okay. What else here? You will have a 2-lens system. I think those are pretty simple. They just take a little time to work through. But remember, you just it'll be a simple 2-lens system, not all squished together like we did, but one where there's no virtual objects. Won't see any of that because you didn't have that on your test.
Is Q ever negative?
Yeah. No, Q is negative if you have a virtual image. Yeah, I think in fact on one of the tests there was a negative Q. I forget which one it was. Q can be negative if you have a system where you have your 2 lenses, your object is here, and your image is here. If this image is within the focal point of this lens, like if it sits like that, then you're going to come up with a negative Q. Right, because if my object is inside the focal point, I get a virtual upright image. Negative Q means you get a virtual image. But with a 2-lens system, don't worry about it. Just whatever it comes out as, that's what you use. But make sure you track your signs along really well. All right. And also don't forget your magnification is negative Q over P. So if you come up with a negative Q, then your magnification is going to be positive. Virtual images are always upright, except for a two-lens system. Right? So, you want me to explain that? Okay, so virtual images are always upright. So for example, if I have a system like this, I have an object there, my image will be there. That's my object, that's my image. Virtual images are always upright. But in this case, this is my object. And now the object is inverted, so that means that the image is going to be inverted too. Virtual images are always the same orientation as their object, is maybe a better way of saying that. They're not flipped from the objects. Okay? But yours is going to be straightforward. Straightforward, nothing fancy. Two-lens system. Camera can focus on different objects by changing the distance between the lens and the film. When is this distance the largest? So this actually incorporates not only cameras, but the eye too. So let's go over both of them. For a camera, I have a lens and a film. The focal length of the lens never changes, right? So if I have something that's really far away, that means the rays are parallel. They'll focus at the lens, at the film, or the CCD, or whatever it is. And in this case, if the object's really far away, the film is at the focal point. All right. Now, if I have however, if I have something that's closer, I move the film further away. Here, let me redraw it differently. I move that film far away. My focal point's still the same, but if I have something closer, I draw my rays here. I want my rays to cross at the film. So in that case, I have to move the film back for something that's closer. Now with the eye, a similar thing occurs. This is the eye. If I'm looking at something really far away, this is my focal point. My focal point is at the retina. But if I'm looking at something nearby, my focal point has to be closer. So far away, long focal point. Nearby, short focal point. Knowing your ray diagrams will help with that, because you'll be able to look at the rays and how to draw them. All right. I don't want to rush out. I'm going to have to leave in about 10 minutes. So. Okay. Actually, give me 2 minutes. I'll be right back. Okay? So y'all think about the other questions I have. I'll be right back. Sorry. We're going home with this. We're going to home. Yeah. We don't go to home very often. What's closed?
Charlotte's Food.
The what?
Charlotte's Food.
What's that?
It's an ice cream shop. It's really good. Really.
The one down on Barrow Street?
Yeah.
I've been to that one. We went
Closed
once.
down because of the all ice cream stuff going on.
Oh.
It's stereo ice
We're going to get a cat. Oh, we're going to look at cats.
Oh, nice.
My daughter got a cat for her birthday. Or she got the promise of a cat for her birthday. She got like a kitty litter box and a food bowl and stuff like that. She's very excited. She's getting a cat. 17, yes. Okay, yeah, so two waves of wavelength 4 meters travel through space. The first wave travels 8 meters, second wave travels 10 meters. What type of interference occurs? What's important here is the path length difference. If you have a path length difference that's a wavelength, or 2 wavelengths, or 3 wavelengths, or whatever, that's constructive interference. If you have a path length difference of half a wavelength, that's destructive interference. So here, this wave travels 8 meters, this wave travels 10 meters. 10 minus 8 gives us our path length difference, that's 2. The wavelength is 4, so 2 is equal to half of a wavelength. Right, 2 is equal to 4 over 2. So it's a half a wavelength. So these two waves look like this. The second wave, when it met up a half a wavelength later, looks like this. This gives us total destructive interference. This question may or may not be on the test, but the concept of path length difference giving us a constructive or destructive interference will definitely be on the test. I'm pretty sure this one or a similar one is on it too.
If it was 3, it would be neither.
Right, if it was not a full wavelength or not a half wavelength, yeah, it would be neither constructive or destructive, but something in between. Both would actually occur. All right, is that clear? Okay. You'll see that, okay? You're going to see, it comes up a lot on this one, right? Like this one, that was a similar question. This one is a similar question. Yeah. So this is another one of those where you have to change the variables. So single slit, you increase the width of the slit. So I'll start with this, A sine theta equals M lambda. I increase the width of the slit, so that goes up. And now I want to know what happens to the width of the central bright fringe. Well, if that goes up, theta has to go down. That means that the width of the central bright fringe gets narrower. If theta doesn't, imagine here I have my pattern. That's saying that this angle theta is getting smaller. So if that angle theta gets smaller, that means that central bright spot gets skinnier, it gets narrower. Does that answer your question? Yeah? All right, what else, folks? All right, mirror produces an upright image. The object is 2 centimeters high, the image is 8 centimeters high. So then you want to think, well, the image is bigger and it's upright than the object. That means that this is the scenario that I have. I have an object here, the image is here. It's a concave mirror, all right? The radius of curvature is 16 centimeters, so the focal length is half that, is equal to 8 centimeters. It's positive because it's a concave mirror. But if it was negative, I wouldn't tell you that, you just have to know, all right? So if it was a convex mirror, it would be negative. I know that my magnification is equal to positive 4, 8, and 2, and it's upright. That's where I get that. The image height, 8 centimeters, over the object height, 2 centimeters, gives me 4. And this is further equal to negative Q over P. And then I want to know where is the object located. So I want to know what is P equal to. So now you have to do a system of equations. I say 1 over F, that's 1 over 8, equals 1 over Q plus 1 over P. I'm looking for P, so I want to get rid of this Q. And I'll do that through this. I'll say Q is equal to negative 4P. And I take this and I plug it in there. So I get 1 over 8 equals 1 over negative 4P plus 1 over P. Am I doing this right? Yep. All right, and then I solve this for P. This becomes 4 over 4P, so I get 1 over 8 equals 3 over 4P. D is the right answer. You're going to have a question like that. You will have to solve a system of equations like this. Okay, it's probably the most complicated algebra, but it's not terribly complicated. It's a simple system of equations as far as systems of equations go, but you will see one like that. Be a little bit different, so don't just memorize this one, but just make sure that you know how to do this, solving this system of equations. Is that clear? All right, there are two different variations of that. Look back at the old test, and then also look back previous tests so you can find samples. What else on this test? Okay, you have to look at two different things here. For double slit interference, first, d sine theta equals m lambda. Yeah, and then y, is it not? I think it is, but it's just sort of a little bit different. Yeah, it's on here. It's this, but it's a little bit different. All right, because it takes. Yeah. Yeah, but that's not quite good. I mean, yeah, you can. So remind me, I'll put it up on the board. Punch and test. Okay. I've already printed out your exam, so I can't put it on there. But or you can just remember y equals L tan theta. But if you remind me, all right, online students too, y'all remind me. I'll put it up on the board for y'all. So here, if I double the separation between the slits, that means I get half here for sine theta. If I have that sine theta, I also have this tan theta. And if I have that, I have the y. So B is the right answer. The distance between the slits gets smaller. All right? What else? Everybody got this one, I'm pretty sure. And this one too. Actually, some people put C, which messed me up. So, what was A? I meant for it to be A. But most people put A. But some people put C. They still got it right. A and C are the same. All right? Is that all, y'all?